Algebraic Structures, Lecture 20, Finite Fields. The aim for today's lecture is to classify and construct all finite fields. Recall that if f is a finite field, then the characteristic of f must be a prime number. So a prime which is greater than 0. This means that the identity element 1 in f generates a subfield of f which is isomorphic to the elementary field z sub p. In particular, this means that f is a finite-dimensional vector space over zp, which implies that the cardinality of f is some power of p. So the cardinality of f is p to the power n for some n. Also, we have the so-called Frobenius map, which sends an element x in f to x to the power p. And this is a field homomorphism from f to f, and since f is finite, it's actually an automorphism. So we will denote this map by phi. Now we are ready to formulate our main theorem, which is due to E.H. Moore, and he proved it in 1893. Claim 1. For any prime p and any positive integer n, there is a unique, up to isomorphism, field f Pn with p to the power n elements. Claim 2. If k divides n, then f p to the power n has a unique subfield isomorphic to f p to the power k. Claim 3. The extension from f sub p to the power k to f sub p to the power n is a Galois extension whose Galois group is cyclic and is generated by the case power of the Frobenius map. And claim 4. The multiplicative group f sub p to the power n upper star is cyclic. In particular, the field f sub p to the power n is equal to the field which is obtained from f sub p to the power k by joining any generator alpha of this multiplicative group. Let's go to the proof of the theorem, and we start the proof with a construction of a field with cardinality p to the power n. We consider the polynomial f sub n of x, which is equal to x to the power p to the power n minus x. So that's a polynomial over zp. Note that the derivative of this polynomial is equal to minus 1. So we have p to the power n times x to some power minus 1, but p to the power n is actually 0. So we just get minus 1. Minus 1 is non-zero, which means that the greatest common divisor of fn and its derivative is equal to 1. And this means that fn doesn't have multiple roots. Now let us define the field capital F as a splitting field of our polynomial f sub n of x over the field z sub p. Let little k be the subset of this capital F, which consists of all roots of the polynomial f sub n of x. Then, of course, since our polynomial has degree p to the power n and doesn't have multiple roots, it follows that the cardinality of this k is p to the power n. So we claim that this k is a field. Note that an element alpha belongs to k if and only if the nth power of the Frobenius applied to alpha is equal to alpha, because the nth power of the Frobenius applied to alpha is exactly alpha raised to the power p to the power n. So in particular, first of all, we immediately see that both 0 and 1 are elements in this k. Also, since phi to the power n is a homomorphism, for any two elements alpha and beta in k, Applying phi to the power n to their sum, we get phi to the power n applied to the first element plus phi to the power n applied to the second element, and this is equal to the first element plus the second element. So this means that alpha plus beta belongs to K. Similarly, applying phi to the power n to the product of alpha and beta, we get phi to the power n of alpha times phi to the power n of beta, which is equal to alpha beta. So K is closed under the product of two elements. So this implies that K is a subring of F. Next, if alpha is K is a non-zero element, then by definition alpha to the power p to the power k is equal to alpha. If we divide by alpha, we get alpha to the power p to the power k minus 1 is equal to 1. And this means that the inverse of alpha is equal to alpha to the power p to the power k minus 2. But that's an element in K. And this means that K is a subfield of F. And this proves our claim. So now, by definition, Fn of x splits over K, and therefore the capital F should be equal to K. So we have now constructed our field capital F sub p to the power n with p to the power n elements. Now, if capital K is any field with p to the power n elements, then the cardinality of the multiplicative group of K should be p to the power n minus 1. And therefore, by Lagrange theorem, for any element alpha in this multiplicative group, alpha raised to the power p to the power n minus 1 should be equal to 1. And this, of course, implies that alpha raised to the power p to the power n is equal to alpha for any alpha in K. And this means that K must be the splitting field of F sub n, because the splitting field is unique. And this completes the proof of claim 1 of the main theorem. Let us now prove part 2. Assume that K divides n. If alpha is such that alpha raised to the power p to the power k is equal to alpha, then for any I greater than or equal to 0, alpha to the power I raised to the power p to the power k is equal to alpha to the power I. So in particular, alpha raised to the power p to the power n is equal to alpha raised to the power p to the power n minus k, and then raised to the power p to the power k. So this, by our previous computation, is equal to alpha raised to the power p to the power n minus k. Continuing similarly, we will end up with alpha. And this means that each root of the polynomial fk is also a root of the polynomial fn. In particular, fk splits over our field f with a lower index p to the power n. And this means exactly that f sub p to the power k is a subfield of f sub p to the power n. This subfield is unique, as fk has exactly p to the power k roots. And this completes the proof of claim 2 of the main theorem. Now let us prove claim 3. The extension from f sub p to the power k to f sub p to the power n is normal, since f sub p to the power n is the splitting field of a certain polynomial. This extension is separable because this polynomial, and that's the polynomial fn, doesn't have multiple roots. And together, this means that our extension from f sub p to the power k to f sub p to the power n is a Galois extension. And the cardinality of the Galois group should be, of course, the degree of this extension, so that's the dimension of f sub p to the power n over f sub p to the power k. And that's n divided by k. Clearly, the case power of the Frobenius map belongs to the Galois group, because it fixes the elements of f sub p to the power k by definition, and we can treat it as an automorphism of f sub p to the power n. Also, the smallest power of this case power of phi, which is the identity on f sub p to the power n, is the power n divided by k. So that's exactly the nth power of the Frobenius. So it is equal to the case power of the Frobenius raised to the power n divided by k. And that's because the ith power of the Frobenius has at most p to the power I fixed points for all I. And this means that phi to the power k has order n divided by k in our Galois group. Since our Galois group has cardinality n divided by k, it follows that phi to the power k generates this Galois group. And this completes the proof of claim 3 in our theorem. Finally, let us discuss the last claim, that is the cyclicity of the multiplicative group of a finite field. Consider the multiplicative group of the field f sub p to the power n. This is a finite abelian group of order p to the power n minus 1. Let Q be a prime number dividing p to the power n minus 1. Consider the CIL of Q subgroup GQ of our multiplicative group. Assume that this CIL of Q subgroup has order Q to the power n for some n. Then, of course, by Lagrange theorem, taking any element alpha in this CIL of Q subgroup, raising this element to the power Q to the power m outputs 1. Using the classification of finite abelian groups, we can write this finite abelian group G sub Q as a product of the cyclic groups zq to the power m1 times zq to the power m2 times and so on. So the last factor will be z, q to the power mr, and r is a positive integer greater than or equal to 1. Let us denote by m prime the maximum of all these exponents m1, m2, and so on mr. And note that m prime is smaller than m if and only if r is greater than 1. Of course, for any element alpha in GQ, alpha raised to this power q to the power m prime is equal to 1. At the same time, the polynomial x to the power q to the power m prime equals 1 has at most q to the power m prime roots. Therefore, m should be equal to m prime, because in GQ we have q to the power m, roots of this polynomial. And this implies that r is equal to 1. So our CIL of Q subgroup GQ is cyclic. And then, by Chinese remainder theorem, this implies that the whole original abelian group f sub p to the power n star is cyclic. So we have proved that the multiplicative group of a finite field is cyclic. And of course, if we take any generator of this group, then we can get the bigger field by adjoining this unique generator to the smaller field. And this completes the proof of claim 4, and hence of the whole main theorem. Here is a consequence. Corollary: for every prime p and every positive integers n and k, there is an irreducible polynomial over f p to the power k of degree n. Proof: consider the field extension f sub p to the power k to f sub p to the power n times k. Let alpha be a generator of the cyclic group f sub p to the power nk star. Then the bigger field f sub p to the power nk is obtained from f sub p to the power k by adjoining our alpha. Consider the minimal polynomial of this alpha over the smaller field f sub p to the power k. This polynomial must be irreducible because it's a minimal polynomial of an element. And the degree of this polynomial is exactly the dimension of the bigger field over the smaller field. And this is nk divided by k, which is n. And this completes the proof of the corollary. Here is an example. Let us construct a field with 4 elements. 4 is 2 to the power 2, so we should be looking for a degree 2 extension of the primary field Z2. And for this, we need an irreducible polynomial over Z2 of degree 2. We can list all polynomials over Z2 of degree 2. There are 4 of them, because Z2 has just 2 elements, so we can only choose the free term and the coefficient at x. So our polynomials are x squared plus x squared plus 1, and x squared plus x plus 1. The polynomial x squared is x times x, so that's reducible. The polynomial x squared plus x is x times x plus 1, that's reducible. The polynomial x squared plus 1 is actually equal to x plus 1 times x plus 1, because 2x is equal to 0 over Z2. So this is also a reducible polynomial. And we claim that the remaining polynomial x squared plus x plus 1 is irreducible. Since this polynomial has degree 2, it is enough to check that it doesn't have any roots. So if we insert x is equal to 0, we get 0 squared plus 0 plus 1, that's 1, not 0. If we insert x is equal to 1, we get 1 squared plus 1 plus 1, this is 1, not 0. So our polynomial doesn't have any roots, it has degree 2, so it is irreducible. And so our field with 4 elements, f sub 2 to the power 2, is isomorphic to the quotient of the polynomial algebra over Z2, this should be Z2 of x, modulo the ideal generated by the polynomial x squared plus x plus 1. So the elements of our field with 4 elements are in bijection with all polynomials over Z2 of degree 0 or 1, including the 0 polynomial. So our field with 4 elements consists of the classes of 0, 1, x, and x plus 1. So we denote a class of fx by fx overlined. So fx overlined is fx plus our ideal generated by x squared plus x plus 1. It is very easy to write the table for addition of these elements. So 0 plus 0 is 0, 0 plus 1 is 1, 0 plus x is x, 0 plus x plus 1 is x plus 1. And similarly, that's a commutative operation, so the first column is similar. 1 plus 1 is 0, 1 plus x is x plus 1, and 1 plus x plus 1 is x. And similarly in the other order. X plus x is 0, x plus x plus 1 is 1, and finally x plus 1 plus x plus 1 is 0. And so we see that the additive group of our field with 4 elements is isomorphic to Z2 times Z2. Now, in order to determine multiplication, we need to compute. First of all, x times x is equal to x squared. So, and modulo the ideal, so x squared plus x plus 1 is equal to x plus 1. So we get the element x plus 1, its class. Similarly, x times x plus 1, that's the same as x plus 1 times x, that's the class of x squared plus x, and correcting modulo the ideal, we see that x squared plus x squared plus x plus 1 is equal to 1. And finally, x plus 1 times x plus 1, that's of course x squared plus 1 because 2x is 0, and then again adding the generating polynomial of the ideal, we get x. So here is the multiplication table in our field. Of course 0 multiplies everything to 0. Of course 1 is the identity, and then the non-trivial multiplication is that x squared is equal to x plus 1, x plus 1 squared is equal to x, and x times x plus 1 is equal to 1 in both directions. So we see that the multiplicative group of our field with 4 elements has 3 elements, 1, x, and x plus 1. So this is isomorphic to the cyclic group of order 3, and so it's generated by any non-identity element. So both x and x plus 1 generate this multiplicative group. We also see that Z2 is a subfield of our field with 4 elements when we look at Z2 as the classes of the scalar polynomials. So F2 consists of the classes of 0 and 1. The Frobenius map phi, of course, fixes 0 and 1 and swaps x and x plus 1. So the Galois group of F4 over F2 consists of the identity and of the Frobenius map phi. So that's a cyclic group of order 2 generated by phi. Okay, let us also briefly discuss one of the applications of finite fields. Finite fields are widely used in cryptography. So for example, in the so-called BCH codes. Here is a rough description what that means. Let p be a prime number and m and d be positive integers such that 2d plus 1 is less than or equal to p to the power m minus 1. Consider the finite field f sub p to the power m and its multiplicative group f sub p to the power m star. Let alpha be a generator of this multiplicative group. For I greater than 0, we have the irreducible polynomial over Zp of the element alpha to the power I. That's some irreducible polynomial over Zp. We define the so-called generator polynomial of our code as the polynomial g of x. It depends on m and d, and we define it as the least common multiple of the polynomials, the minimal polynomial of alpha, the minimal polynomial of alpha squared, all the way up to the minimal polynomial of alpha to the power 2d over Zp. So by construction, our polynomial divides x to the power p to the power m minus 1 minus 1, because all powers of alpha are roots of this polynomial x to the power p to the power m minus 1 and then minus 1. Let r be the degree of g of x, so of course it depends on d heavily. Let n be p to the power m minus 1. The input datum for our code is a string of n minus r elements of Zp, which we can interpret as coefficients of the polynomial f of x over Zp of degree at most n minus r by sending the vector of our elements a0, a1, a2, and so on to the polynomial a0 plus a1x plus a2x squared plus and so on. So how do we encode? We multiply f of x with x to the power r is our degree of g of x, and write the outcome in the following form, so we can divide by our generator polynomial g of x with the rest. So we write x to the power r f of x as h of x times g of x plus u of x, where the degree of u of x is strictly smaller than r. The code word for f of x is defined as x to the power r f of x minus r of x, that is, it is h of x times g of x. So that's the code word for our f of x, which we transmit. So note that the leftmost n minus r coefficients of this code word agree with the coefficients of f of x, and the remaining r digits on the right side are the checksum digits, which we may use to detect and correct errors. So upon reception of our word, we receive some polynomial v of x over zq of degree at most n. And in order to check whether there are some errors or not, we divide this v of x by g of x. Alternatively, we can evaluate v at alpha, alpha squared, alpha cubed, and so on, up to alpha to the power 2d. If all these evaluations give us 0, we treat v of x as error-free, and then we can decode it by deleting the r rightmost terms in v of x. And then we get the original thing which we wanted to transmit. If v of x is not divisible by g of x, this means that v of x has an error. Then we perform an error correction before we decode. Here is a rough idea for p is equal to 2 how the error correction works. We start with the vector v of alpha squared, and so on, v of alpha to the power 2d. and this vector is non-zero if and only if we have an error. Starting from this vector, for each s greater than or equal to 1, we consider the following matrix, Ms. The first row of the matrix is v of alpha squared, v of alpha cubed, all the way up to v of alpha to the power s. The second row is v of alpha squared, v of alpha cubed, all the way up to v of alpha to the power s plus 1, and so on. The last row is v of alpha to the power s, v of alpha to the power s plus 1, and all the way up to v of alpha to the power 2s minus 1. So assume that we know for sure that our transmission can produce at most d errors. Then it turns out that we have exactly u errors if and only if the matrix mu is non-degenerate, while mu prime is degenerate for all u prime that are greater than u. So we can find this u starting from the biggest matrix md, looking is it non-degenerate? If it's non-degenerate, then u is equal to d. If md is degenerate, we go to md minus 1, and so on, and proceed until we detect what the u is. And then, when we know how many errors we are, then to pinpoint the places for errors, one needs to solve a certain system of linear equations in which our matrix mu is the matrix of that system. So it is non-degenerate, so the system has a unique solution, and when we know these places where the errors occurs, we can correct them because we are over the field Z2, there are only two possibilities. If there is an error, we just change the corresponding element to the other element. And this is how this works. Some additional problems and questions at the end. Problem question 1. Determine all irreducible polynomials over Z2 of degree at most 4. Problem question 2. Determine all irreducible polynomials over Z3 of degree at most 3. Problem question 3. What prohibits Z sub 3 to the power 5 to be a subfield of Z sub 3 to the power 8? Problem question 4. Find the generator of the multiplicative group of a field with 27 elements. And problem question 5. Show that every reducible polynomial over Zp divides x to the power n minus x for some n. Thank you very much, and see you next time.